All right, so let's get going on today's class. So today what we're going to be doing is we're going to be continuing our look at problem solving. This is going to be part of our final portion of this course where we're looking at higher level, higher order cognitive abilities. So we're going to be doing problem solving, then we're going to move into judgment and decision making. And we're going to continue with our look here today. But before we get on to problem solving, I do want to draw your attention to one of the homework assignments because it falls outside of the traditional kind of homework solution that we've been using, online solution. Then we'll talk about the information processing approach. We'll give you a brief recap. We introduced that last time. And then we're going to take a look at what psychologists have identified as some of the strategies that we use to navigate this problem space that allows us to solve problems. And we're going to apply those ideas to understand inside problems and why oftentimes they're very difficult to solve, even though they are literally one-step problems. All right, so for the homework assignment. So if you recall in your syllabus, we mentioned that there were, in the homework section, there was going to be a reflecting on homework assignment. We were waiting until we were covering the right material to introduce this. Now is the right time. So this is going to be a two-part homework assignment. Part one is now available. Part two is coming soon. But the first part is reflecting on the gender pay gap. So this is a issue that is facing our society right now. And we just had on April 2nd, I believe it was Equal Pay Day, just a few days ago. So this homework assignment is the first part of this. And what you need to do for this one, it's not in our online textbook portion or in the modules. It's actually in Canvas in the assignment. You'll see this reflecting on part one, the gender pay gap. That's where you access the assignment. And what you do is you just simply click on the following link. It will ask you a series of questions. First question is your name. Put in your name. That's how I will be assigning grades for this particular assignment. So I need to know who has completed it. Then you will be randomly assigned to one of two articles. I was thinking about assigning both of them, but I didn't want to overwhelm you at this time with another massive homework assignment. So you'll be randomly assigned to one of two articles, and then there will be a series of questions regarding those articles, multiple choice questions. There's 3 per article. So it's a pretty straightforward assignment, but just be aware that it is available in Canvas. So this is not in your online textbook e-text modules. This is on Canvas, and you access it by clicking on that link. It will take you through the assignment, and and that is part one of our reflecting on assignment. That is going to be due Monday, April 15th by midnight. So you have until midnight just before the next class. And then what we're also going to do is on Tuesday, I will also give you details about part 2 of this. So we have part 1, and then there's going to be a follow-up homework assignment, which is coming soon. And that is going to be our reflecting on homework assignments that we were, that was in the syllabus. Mm-hmm.
When are we going to get our test grades back?
You are going to get your test grades back probably next class.
Okay.
Yeah. There's been a slight delay in just getting them graded, but I do have them on. We'll be doing that.
Okay.
Yep. Any other questions? All right. Okay, so we're going to continue on with our information processing approach. So remember we introduced some new concepts, new ways of thinking about problem solving, new ways of kind of being able to analyze what is it that we do when we're solving a problem. So the key idea was that problems can be represented in terms of a problem space. So there's this idea of a problem state, that is where it's a representation of where you are in the problem. What is the current situation that you have in the problem that you're trying to solve? This can be an initial state, which is the starting of the problem. It's where you are when you start the problem. Also included is the goal state. That is where you're trying to get to. That is the goal of the problem. Once you reach the goal state, problem solved. That is literally the solution to the problem. And then in between those, are intermediate states, and this is the problem at various levels of solution, right? So for the Tower of Hanoi problem, this is when you have the disk spread out. You aren't at the start state, you aren't finished, you're somewhere in between, you're at an intermediate state. And then there was the idea of the problem space, which is a visual representation of the states and how you can get from one state in the problem to another state. So it's the various states and the relations between them. And those relations are known as operators. Literally things that you can operate on the problem with, moves that you can make in the problem, ways that you can solve this problem. Those are the operators, and technically speaking, they're ways of moving between the different states. So we have a problem space. This is only part of it for the Tower of Hanoi. We have an initial state up here. We want to get down to a goal state down here. And we do that by applying an operator and moving to an intermediate state. And then we apply another operator and move to an intermediate state. And then we apply another operator, another intermediate state. And by applying operators, legal moves, things that we can do to solve that problem, eventually we can get down to the goal state, and that is a solution to the problem. That is when we have problem solved. So in this approach, one of the key ideas or key questions is, how do we navigate this particular problem space? How is it that we search through that problem space in order to go from this initial state down to this goal state? Because most problems that we face, most of the things that we try to solve, remember, they're not immediately obvious. The solution is not immediately obvious. One thing that implies is that we don't have a full view of the problem space. Because if you ever have a full view of the problem space, then solving the problem is easy, right? If I gave you this problem space here, and I said, how do you go from the initial state to the goal state? You simply say, well, it's right down there. Pretty easy, pretty straightforward, pretty obvious, right? This is not a problem when you can see the whole problem space. So what happens when you can't see the whole problem space? How is it that we navigate through these problems to try to get to the solution? That's what we're going to be focusing on for most of today. All right, so we're going to start off with another problem that has another problem space, and this is called the Hobbits and Orcs problem. And I'll read it out to you, and then I'll give you some time to try to figure this one out. So the Hobbits and Orcs problem goes on one side of a river are 3 Hobbits and 3 Orcs. They have a boat on their side that is capable of carrying 2 creatures at a time across the river. The goal is to transport all 6 creatures across to the other side of the river. At no point on either side of the river can Orcs outnumber Hobbits, or the Orcs would eat the outnumbered Hobbits. The problem then is to find a method of transporting all 6 creatures across the river without the Hobbits ever being outnumbered. So this is the situation. You got your river right there. You got your boat. You got your Hobbits. You got your Orcs. And what you want to do is you want to go from this initial state where you have all 6 creatures on one side, and you want to get it to the point where you're at this goal state where you have all 6 creatures on the other side of the river. And the key here is that somebody has to be in the boat in order for it to cross the river. Once you cross the river, everybody gets out of the boat. And at no time can you have more Orcs than Hobbits on either side of the river. Otherwise, the Orcs will overpower the Hobbits, and it's game over. So what you can do, for example, is on that first move, you can say, all right, I'm going to put 1 Orc and 1 Hobbit into the boat, and I'm going to take it across the river. So you got 1 Hobbit, 1 Orc in the boat, you take it across the river, and now the question is, what do? You got to put somebody in the boat to get it back. Once you get it back, who then goes into the boat? And remember, one of the key things here is that not only can you not have more Orcs and Hobbits on either side of the river at any time, you always have to get out of the boat. So you can't have a Hobbit staying in the boat saying, oh, I'll take you across, but I won't get out. They both have to get out of the boat. All right, so that is the problem. That's one of our intermediate states. So now the question is, how can we do this? So I'm going to give you some time to try to figure this out. So remember, we are in our initial state over here, trying to get to the goal state over here, and I will give you a few minutes to try to figure out what are the steps in order to do that. So write down in your notes, step 1, Orc and Hobbit go across. Step 2, somebody goes back. Step 3, somebody goes across. And let's try to figure out how to get all 6 across safely without violating any of the rules. Oh yes, you can only put 2 in the boat. So either 2 or 1 in the boat at all times. Otherwise, you can just pop all 6 in the boat. Everybody goes across. Problem solved. All right, we're about 1.5 minutes in. Does anybody have a successful solution yet? Anybody get all 6 creatures across? I'll give you a little bit more time. All right, were there any successful solutions? Did anybody get close? Maybe get 4 across? Anybody get any across? All right. Maybe it's a little bit too early for a full solution. All right, so looks like nobody got to the goal state. And one of the reasons this was chosen is because it illustrates a very nice principle about how we solve problems. And specifically, there's one move that when you're trying to solve this problem is typically the most difficult problem. So to start it off, you might start it off with saying, all right, I'll take an orc and a hobbit across. And then notice that once you're in this intermediate state, your next move is pretty straightforward because there's nothing else you can do here except send that hobbit back. Because if you send the orc back, then the orcs outnumber the hobbits, it's game over. So you got to send the hobbit back. So then what do you do? How do you solve this? You know, do you send 2 orcs over? So there's one way to kind of solve it. So let's go through that solution right now. So we sent the hobbit back. We're good. 3 hobbits, 2 orcs. Nobody is getting eaten. At this point, we have to send 2 people over again. So we send over 2 orcs. So far, so good. 3 hobbits and 2 orcs. Now we got to send back 1 orc. Then once again, we kind of have this situation where there's nothing else that we can do except send over 2 hobbits. So we send over 2 hobbits. And then if you were writing out your steps, this is probably where you got stuck. This is probably the point where you weren't able to take the next move in the problem space. And the reason for that is because this is the step where instead of sending 1 person back, you got to send 2 individuals back. So in this next step, you got to send back 1 hobbit and 1 orc. And then you can send across 2 hobbits. Then you can send back 1 orc, 2 orcs, send an orc back, get the last 2 orcs, and you've arrived at your goal state. So this problem here is difficult because of that one move. That's usually where subjects doing this problem will encounter that difficulty. So let's take a look at the problem space for this. We have our initial state. And from that initial state, there's a few operators that you can apply. There's a few legal moves that you can do. So for example, you can send across 2 orcs. That stays within the limits of the problem. That's a legal move. You send over 2 orcs. Or you can send over 1 hobbit and 1 orc. Or you can send over 1 orc. All right, so this one doesn't really make much sense because you'll just end up sending that orc back anyway. But those are your 3 first moves. Those are the moves that you can do, and those are the only moves that you can do. So let's continue on with this situation here. So from that, you have to send back a hobbit. So notice in the problem space, you're actually constricted by your operators. There is no other move that you can do here, no other intermediate state that you can reach from here, except to send back that 1 hobbit. You could send them both back and go back to the initial state. But again, that's something that we'll see we tend not to like to do. So once we send over that 1 hobbit, we then again have to send over, in this case, we send over the 2 orcs. And from there, we send back the 1 orc. And then this problem space actually gets kind of long, so we send back the 2 hobbits. And then from there, this move here is the one that is the most difficult to get to. That's the operator that's the most difficult to apply because we have to send back an orc and a hobbit. And notice that there's really nothing else that we can do. We can back up and just go back to this situation here. Just say, well, sorry, we can back up and just go back to this situation here and say that we sent across 2 hobbits. We can just bring back 2 hobbits. We can undo what we did. Or once we get here, we can go forward, but we need to. The only thing we can do here is to send back a hobbit and an orc. That's the only move that will not end in game over. So it's interesting that in this problem space, even though that's the only thing that we can do, we still have difficulty identifying that move. We still have difficulty identifying that operator and navigating the problem space. And then from there, it's pretty straightforward. We send across the 2 hobbits, send the orc back, send across the 2 orcs, send another orc back, until we finally end up at the goal state. So that's a part of the problem space that we've been navigating. So the question now becomes, why is this problem hard when just about every single move is constrained? You don't really have a lot of options for every single move. There's only one way to take people across and not have more orcs and hobbits on either side. And especially, why is this move, where we got to take back 2 individuals, so difficult? Well, psychologists have identified what they call strategies for operator selection, which are ways that our minds work, ways that we think when we're going through trying to solve a problem. These are strategies that we have developed that allow us to solve a problem. And one of the strategies that we have is called backup avoidance. And in backup avoidance, we tend to not want to select an operator that undoes the effects of previous operators. We tend to avoid that kind of a move. So when you're doing, for example, the Tower of Hanoi and you have your problem space, you tend to apply operators that get you closer to the goal state, that take you closer to where you want to go. And then you avoid operators that bring you back, that undo the operations that you've currently done. You take that and you're mentally, you don't even think of that. So for most of you, if you're doing the Tower of Hanoi and you ended up at this location here, most of you wouldn't even think of putting that green disc back on top and just restarting it, because this operator here, even though it's a legal move, that would undo the effect of all your previous operators. And we, as a heuristic, as a strategy, have that idea that we want to avoid this backup, this undoing of operators. That's known as backup avoidance. Another thing that we do is called difference reduction. So actually, before we go to we leave backup avoidance, this is why probably when you were solving the hobbits and the orcs problem, you never once to yourself said, I'm going to take a hobbit and an orc and I'm going to go across, and then I'm going to take a hobbit and an orc and I'm going to go back. And then I'll go across with a hobbit and an orc, and then I'll take that hobbit and an orc and I'll bring it back. We don't do that solving problems. Legally, we could. It follows the rules. It doesn't contradict anything. But we don't select operators that undo the effects of any of our previous operators, any of our previous moves. All right, the next one, difference reduction. We tend to select non-repeating operators that most reduce the difference between the goal state and the current, your current state and the goal state. So what we tend to do is we tend to select the move, select the operator that makes the biggest difference in getting us from where we are to where we want to go. It doesn't get us all the way to where we want to go, because that's solving the problem. But if we have a choice between 2 operators, and one of us gets us a little way towards the goal, and the other one gets us a longer way towards the goal, we will tend to choose that one that reduces the difference the most. So this difference reduction is, again, a strategy that we use that typically works, but doesn't always, and that's what makes some problems difficult. And this difference reduction is also known as hill climbing, so called because of a strategy for finding the highest point in a field if you're blindfolded. So if you ever wanted to find the highest point in a field when you were blindfolded, right? Say you were out somewhere and there were hills all around you, and somebody blindfolded you and said, go find the highest point. What you would probably do, one strategy that you would be able to do, is you would be just maybe take a step in every single direction, right? You would take a step here, take a step here, take a step in that direction. And what you would do is you would kind of measure which one of those steps took you the highest up. Because you want to get to the highest point. So which one of those steps made the biggest difference between your lowest, your current state, which is the low point, and your goal state, which is the highest point. And if you find a direction that goes up the most, you step in that direction. And then once again, you step in all 4 directions. Follow the one that gets you the highest up. Do that over and over and over again until you come to a point where you step in one direction and it goes down. You step in another direction, it goes down. You step in a third direction, it goes down. You step backwards, it goes down. If every other direction is going down, you're at the top of a hill. At that point, you take off your blindfold, and you're definitely at the top of a hill, but this is a heuristic. This is just a strategy, because you might look around and say, well, I'm at the top of the hill, but I missed that hill over there. I didn't get up to that peak there. So it's not perfect. It's a strategy. It's a heuristic. It's known as hill climbing. And we're going to see that this hill climbing paired with backup avoidance is what makes it very difficult to solve this Hobbit and Orc problem. So we have our initial state there. We're going to here on the y-axis here have the amount of goal, right? How much of the goal have we achieved, right? So in the initial state, we're at 0. We have 0 of the goal achieved. We want to get all 6 Hobbits and Orcs to the other side. Right now we got 0. We're 0 out of 6. And on the x-axis there, we're going to have the moves that we've done, right? So how many moves in are we towards solving this problem? All right, so we initially start, we'll call this move number 1. So move number 1 is our goal state. And so far we got nothing, right? We got no solution whatsoever. We got 0 people on the other side. We make our first move, and we take 2 individuals. We take a Hobbit and an Orc, pop them in the boat, and we go across to the river. Now at this point, after that first move, we have solved this problem a slight amount, right? We have reduced the difference between the solution and where we are right now. So this was our first step in our hill climbing. We have gotten closer to the solution, and that is one of the reasons why that move is chosen. So you could have sent 1 Hobbit across. You could have sent 1 Orc across. You couldn't send a Hobbit across. You could have sent 1 Orc across. You could have, or you could have sent 2 individuals across. Those are your 2 choices. And we chose 2 individuals. And you probably didn't even think of sending 1 individual because, again, we tend to choose the operator that makes the biggest difference. This makes a difference of 2 rather than 1, so we tend to choose this one here. All right, so now we're at this solution here. We got 2 out of 6. And what we need to do is we need to send 1 individual back, send 1 person back with the boat. And notice that this actually, even though we're getting closer to the eventual solution, in terms of the amount of goal that we've achieved, this actually unsolves the problem a little bit, right? Because we used to have 2 on the other side, 2 out of 6, not bad. Now we only got 1 on the other side, 1 out of 6. We've taken a step back. So we've gone up 2, we've taken 2 steps forward, we take 1 step back. But that brings us to a new position where we can now apply an operator again and go 2 steps forward. So we now take 2 Orcs, pop them in the boat, they go across. We end up in this intermediate state right there, and now we have 3 out of the 6 creatures across. We're halfway there. We reduced the difference between our initial state and our goal state. We're now at 3 out of 6. All right, so that's our current goal state. Then what we do is we pop an Orc into that boat. We take it back. Once again, we've gone 2 steps forward. Now we got to go 1 step backwards. So we went 2, we went back 1. We've actually, again, unsolved the problem a little bit on our way through this problem space. So now we take 2 Hobbits, bring them across. Now we got 4 out of 6. Now we're past the halfway point. We got 4 out of 6 on the other side. That's our current state. Now is where the tricky move occurs. So in the tricky move here, you got to take 2 individuals and bring them back over. You got to undo basically everything that you have just done. You have to undo that move where we finally got 4 across and go all the way back to 2 across. So that's the operator that you have to do. And notice it unsolves the problem. It undoes a lot of the operators to a great extent. However, once you do that, you can then move 2 Orcs across. We're back to 4 out of 6. Move 1 Orc back. We're back to 3 out of 6. 2 Orcs across. We got 5 out of 6. 1 Orc back. We got 4 out of 6. And then finally 2 Orcs across. We got 6 out of 6. We have our problem solved. So once we get to here, you can see that we have in our problem space climbed this hill, right? In our problem space, we've climbed the hill from no solution to a complete solution. We made it to our goal state. And if you have written down your steps, you probably noticed that you were doing fine right up until this point. If you got stuck, this is probably where you got stuck. And it's because of that backup avoidance. It's because of that difference reduction. We did not want to apply an operator that took us completely, that undid completely the progress that we just made. And also, when we were looking at which operators can we apply, we kept looking at operators where we only took one individual back, because that would keep us the closest to our goal. That would have the most difference reduction. So this move here is the one that's very, very difficult. And psychologists have used problems like this to identify the fact that we, when we're solving our problems, really dislike taking a step back and taking, undoing some of the operators that we've been using. All right, any questions about that? Okay, so this is actually one of the, well, two things I'll mention about this. This is actually one of the reasons why people oftentimes don't want to back up off of a strategy and change their plans. So I have had, especially in my statistics class, we use a lot of software programs. We use Excel, we use SPSS, and these programs massively speed up your ability to do your statistics homework. It's literally, night and day. It's exponential. You're not faster than a computer, especially at math. So sometimes it's very surprising when I find that students are just not practicing Excel. They're not putting in the time that is required in order to do Excel. And when I see their notebooks, I can see hand calculations all the way down. And I wonder to myself, why are they doing these hand calculations? And the reason for that is because they have this backup avoidance. They're trying to do the most difference reduction. And when they look at the time that they set aside their homework, they take a look, let's say that they have an hour that they set aside for their homework. They take a look at themselves and they say, all right, there's two things I can do in this hour. In this hour, I can either learn how to do Excel and get a little bit of my homework done, because it's going to take me more time to learn how to do Excel and use those functions. Or I can do a pencil and paper and I can get more of my homework done. So they have that decision. Follow this operator, and my current goal to get my homework done, it's only going to get me this far in terms of my homework. Or follow this operator, do a pencil and paper, and I'll get even more of my homework done. So that's why they oftentimes choose that operator. They navigate their problem space of solving homework by saying, I'm going to continue doing pencil and paper, whereas the correct one, even though you're not going to have that big of a difference there, initially you're not going to bridge the gap that much, is to learn Excel so that later you will have those operators to apply to new problems. But we can understand as psychologists why sometimes people will stick with inefficient strategies, inefficient skills, because the time to invest in the new skill takes away from their time to do the actual goal or try to achieve the actual goal, and that keeps people in these inefficient and non-optimal kind of patterns of behavior. So backup avoidance is at play here and in our lives as well. This will be like a little bonus points application moment here. Does anybody know, out of the phenomena that we saw last class, out of the difficulties, the things that make problem solving difficult, can anybody see one of the phenomenon at play in this problem that also contributed to the fact that it was difficult? Mm-hmm.
Probably the mental set, because it worked, like taking one creature back worked for the other steps, but then when you had to change up, your operator didn't work.
Exactly. So one of the reasons why this move right here is also difficult to see is because of that idea of a mental set, because of that idea of applying moves that have worked so far. So if you take a look here and you say, all right, I'm solving this problem, I've never tried anything, let me try this. I'm going to take 2 across. I'm going to bring 1 back. Hey, that seems to have worked. You know, I've gotten 2 across. I've taken 1 back. I've made progress. Next move, going to take 2 across. I'm going to bring 1 back. Hey, that worked as well. You know, I took 2 across. I took 1 back. I've made progress. And that traps you into that mental set. Because now you want to, much like the eggs in a basket, you want to keep doing the same thing. And you're saying to yourself, I think I'm going to solve the whole problem. 2 across, 1 back, 2 across, 1 back, 2 across, 1 back. So that when you have to go 2 across, 2 back, you need to break that mental set. And again, that can make a problem very difficult when you're looking to break those mental sets. So in your own life, apply this in your own life. If you ever find yourself kind of unable to solve a problem, ask yourself, have you been trying to solve this problem in the same way that you have solved the previous steps? And then just ask yourself, what else could I possibly do? What would be like a very different approach to do? Because you might need to break that mental set before you can solve that problem. All right, next up on operator selection. It's the idea of means-end analysis. So means-end analysis, this is again a strategy to problem solving where you create a new goal so that you can apply an operator to that new goal. So you have your original goal. You have a start state and you have an original goal, and you have no way to bridge that gap. So what you do is you create a sub-goal that you can reach, and then that becomes your new initial state, and you continue this process until you solve the complete goal. So one of the really interesting things about a means-end analysis is that it can be recursive. And what recursive means is that it can call upon itself, where you literally kind of do the exact same procedure, just at smaller and smaller increments. So that when you finally solve the small increment, it basically shoots back up and basically like a loop solves itself. So one example of recursion, if you are fans of CSI Miami, you know David Caruso's acting strategy, where you either put your glasses on or put your glasses off, depending upon whether your glasses are on or whether they're off. This is a recursive strategy where you literally call upon the same move, depending upon the state, but it's the same loop every single time. So we're going to see that loop-like structure in means-end analysis when we apply it to a slightly more complicated example. So your goal, transform your current state into the goal state. That's basically saying your goal, solve your problem. Go from the current state to the goal state. So what you might do in a more complicated problem, right? In a problem where we can't really analyze an exact problem space to it, like many real-life problems, oftentimes what you do is you try to match your current state to the goal state to find the most important difference. So you take a look at where you are, you take a look at where you want to be, and you say to yourself, what's the biggest difference here? What's the most important difference? So if you detect that difference, then you have a sub-goal. Now your goal is to eliminate that difference. And if you cannot eliminate that difference, you basically fail the sub-goal of eliminating the difference. If you do eliminate the difference, then you have success. So then you would go back and you would literally do this whole procedure again, because we haven't solved the problem. We've just solved the most important difference. So you then go back and say, well, what's now the most important difference? Difference detected. Eliminate the difference. If you do it, then you go back and you say, well, what now is the most important difference? And you continually just call upon this same procedure to solve your problem. However, if you have no differences, then you have success. But when you have this sub-goal, eliminate the difference, what is it that we do in this procedure here? What is it that we do in that little box there? So for eliminate the difference, what we do is we search for an operator that's relevant to reduce the difference. We literally search for a legal move, a thing that we can do in order to reduce that difference, in order to eliminate the difference between where we are and where we want to be. So we search for it, and if we find it, if we find that operator, if we say, yes, this is the move that I can do, then you you basically apply that operator, and you match the condition of the operator to your current state, once again, to find that most important difference. And if there's no difference, you just apply the operator. You go right ahead and say, this is the move that I can make, and I'm going to make it. If you do detect a difference, however, you then have to eliminate that particular difference. So notice in this means end analysis, it's a continuous analysis where you look for the most important difference, and then you have that sub-goal to eliminate the difference. And then you look inside that sub-goal. How do I eliminate the difference? You find an operator that says, this is what we need to do. If you can apply it, you just apply the operator. If you can't, you have to eliminate the difference that is not allowing you to apply that operator. And if you have success, then once again, you see if you can apply that initial operator. If not, you go back and you search once again for the operator that allows you to reduce the most important difference that allows you to apply the operator that you need to apply. And the thing about this means-ends analysis is that it continually kind of calls in upon itself. We continually keep breaking down our problems into smaller and smaller goals. So if we can't eliminate that difference, then we go to the sub-goal where we search on how to eliminate that difference. And then if we set up a sub-goal where we can't eliminate the difference, we search for a sub-sub-goal where we can eliminate that difference. And then in our sub-sub-goal, if we can't eliminate the difference, we set up a sub-sub-sub-goal where we can eliminate the difference. And eventually we will have success, at which point we can bounce back up here, apply that operator, bounce back up here, apply that operator, bounce back up here, apply that operator, have success, apply the operator, and solve our problem. So that's means-ends analysis. And again, it's this idea of taking that big goal, breaking it down, trying to apply an operator, and then when you can finally apply the operator, builds back up, and you can solve that larger goal. All right, so let's take a look at an example of this, something that will be very important to many of you in the coming semesters. So you want to transform your current state into a goal state. Let's say that you want to go to grad school. You want to transform your current state, which is undergraduate student, into your goal state, which is graduate student, right? So this is a problem that many of you are going to face, right? I want to go to grad school. What do I do? Well, you match your current state to the goal state to find the most important difference. And at this point, you might identify that most important difference as I need to apply to grad school. Actually, the most important difference would be I'm not in grad school, right? Then you would say, well, what's the most important difference there? I need to apply to grad school. That's the most important difference that you have. If you, let's just keep this simple. If you go, what's the most important difference? And there are no differences detected. That would be you realizing that you want to get into grad school and you just realize, oh, wait a second, I'm already in grad school. So you would have success, right? So that's the non-interesting problem. But you need to apply to grad school. So you detect that difference. That's your difference. And now your sub-goal is to eliminate that difference, right? Your sub-goal is to eliminate that difference. If you can apply to grad schools, you got success. Need to apply to grad schools, no difference, and you solve it. If you cannot eliminate that difference, if you cannot apply to grad schools, then you fail. You don't get into grad school. So now this is a sub-goal that you have. You want to eliminate that difference. So what you do is you go into that sub-goal and you search for the operator that's relevant to reducing the difference. So what's the move that you can do that is going to be most relevant to reducing that difference? And in this case, it's complete a grad school application. So you say, I need to apply to grad school. I need to complete a grad school application. That's how you're going to apply to grad school. So we said, well, that's surprising. So we zoom in, right? We want to apply to grad school. So we match our conditions of the current state to find the most important state, the most important difference. You're sitting there saying, my most important difference is to apply to grad school, right? Complete a grad school application. In order to do that, what is now my most important difference? Well, you might realize that you don't have a grad school application. right? You know you got to fill it out, but you don't actually have any. So now your sub-goal is to eliminate that difference. Now your sub-goal is to actually find, some grad school applications. So we zoom in on there. We got no grad school applications. What's your most important difference? You got to find them. So what can we do? What operator can we do? We can Google it. We can go to Google and say grad school programs in psychology. So now we're going to say, all right, if we can Google it, we apply the operator, right? We can reduce the difference. If, on the other hand, we want to do this and there's a difference detected, then we still have to create a sub-goal to eliminate that difference. So if I say to myself, all right, I need to find myself a grad school, I need to find some grad school applications, my next step is to just Google it. What do I need in order to Google it? Well, you need to use your smartphone, right? For most of us, that would be the next move. So once again, you can't just Google it, right? I can't just sit here and say, all right, somehow I'm going to Google this, right? So if I couldn't find anything to do, then I would fail. But if I can find an operator, like use your smartphone, then I can start applying this. And then if I still notice a difference, then I can zoom in one last time and say, all right, I got that, eliminate the difference, in which case you bring your smartphone out of your pockets and you're like, all right, now I can eliminate the difference. So once you do that, once you've completed that sort of means-end analysis, now you can apply the operator to use your smartphone. Once you apply the operator to use your smartphone, then you have that, you apply that operator, then you can bounce back up and Google it. Because now, once you have your smartphone, Googling it is possible. So now you Google it, you apply the operator. Once you do that, you can get your grad school applications. Once you got your grad school applications, then you can apply the operator, finish your grad school applications. Once you complete your grad school applications, then you can apply the operator, eliminate the difference, and actually apply to grad schools. So this means-end analysis is a way that we solve a lot of the problems that we come up in our everyday lives by taking a look at it and saying, what's the biggest difference? What's the most important difference that I need to solve in order to do this? Then you identify whether you can or you can't. If you can't, sub-goal, how can I eliminate that difference and what becomes the new most important difference? And you keep breaking it down into sub-goals until you can finally achieve your sub-goal. And then once you achieve that one sub-goal, every other sub-goal back up the chain becomes possible. And you're able to apply to grad schools in this case and transform yourself from an undergrad student into a grad student. All right, any questions about means-end analysis? All right. So this is one of the ways that the Tower of Hanoi problem is actually solved. It's conceptualized. It's one of the algorithms for solving the Tower of Hanoi problem. It's this idea of recursion. And if you're in computer science, or if you look on, if you ever Googled the program for doing the Tower of Hanoi, it is an extremely short program because literally what the Tower of Hanoi does for any solution is it says to itself, all right, we got this 7-disk problem. So what I'm going to do is I'm going to break this down into a 1-disk on top of a 6-disk problem. Now I got to solve the 6-disk problem. I'm not going to break that down into 1 disk on top of a 5-disk problem. Now I got to solve the 5-disk problem. I'm going to break that down until you get to, I got a 1-disk on 1-disk problem. I'm going to break that down, solve the 1-disk problem. 1-disk problem is just you move that disk, and then it kind of pops right back up the chain. And it's kind of magical to know that the exact same strategy for solving a 1-disk problem is the one that they use for solving, 23, 24, as high as you want to go disk problems. So that's the idea. So if you have a 1-disk problem, if that was your biggest difference, you can apply your operator, problem solved, right? That is the obvious solution. So what if you have a 2-disk problem? Notice that if you have a 2-disk problem, you still have this 1-disk problem. You still have to solve this 1-disk problem. So once you solve that 1-disk problem, you can then solve this other 1-disk problem. You solve this other 1-disk problem, by bringing it over here, and then you can solve your final one-disk problem. Not that difficult. Two-disk problems are just a series of one-disk problems stacked on top of each other. What about a three-disk problem? The three-disk problem is, again, the two-disk problem stacked on top of another disk. So once again, you're in this current situation where you can solve the two-disk problem, ignore this third disk, solve the two-disk problem, and then you just move that third disk over, and now once again you have a two-disk problem to get it over here. So it's that idea of breaking it down into smaller problems and then just calling up on those problems is the way that the Tower of Hanoi is solved, and it's just a very elegant solution that basically says, for this three-disk problem, I'm going to treat it as a two-disk problem, and I'm going to treat that as a one-disk problem, and a one-disk problem solution is obvious, and then you just kind of go back up those sub-goals, and you're able to solve your problem. All right, so we're going to wrap up today by taking a look at insight problems. So we saw this last time. We introduced the idea of the insight problems, and these are problems where people are unaware that they're close to a solution. So the Tower of Hanoi is definitely not an insight problem, because when you are here, you know you're close to the solution. You know you're close to the end game. Applying to grad school is not an insight problem, because after you download those grad school applications, you know you're getting closer. After you check off all the items on the checklist for an application, you know that you're closer. That's not an insight problem. Yep.
Like the hot and cold game would be similar to that. Like someone touches your hot and you're cold and you go hot and then you turn the wrong way. Like you turn and then you're back cold. Is that more like is that more like it too or no?
Hot and cold would also not be an insight problem.
Oh, okay.
Because when somebody says, oh, you're cold, you know that you're far away from solving the problem. When somebody says, oh, you're getting warm, you know that you're closer, right? When somebody says, oh my gosh, you're super hot, you know that you're almost right there. So any problem where you have like this idea that you're getting closer are not insight problems. So things like writing an essay would not be an insight problem, because you know if you need an 8-page essay and you're 4 pages in, you know you're close to solving that problem. If you're finishing up your discussion section, you know you're close to solving that problem. But there are other problems like insight problems where you have no idea if you're getting close to solving the problem. So we saw those, example of 2 of those last time. So the haystack problem is an example of an insight problem. So the haystack was important because the cloth ripped. Why did the cloth ripping make the haystack important? That is a problem where you do not know when you're close to a solution. The haystack became important because the cloth that ripped was a parachute. And once you have that solution, it becomes obvious. We took a look at the funeral problem. About the family funeral, the woman meets the man of her dreams, forgets to get his name or phone number. Nobody else knows who he is. A few days later, she kills her sister. Why did she kill her sister? And again, the answer was that she was hoping that the man would show up to another family funeral. And again, it's a one-step solution, but it's an insight problem where you don't know that you're close to the solution. So why are these problems difficult then? Why is it difficult if you only have the one step to take? Why is it that we have such difficulty solving these problems? And it all comes down to the problem space, right? So this is an example of where knowing what your problem space is can really help us understand psychological phenomenon, like why are insight problems so difficult? And why, again, do we have no idea when we're getting close to a solution? So a researcher here at IU back in the 80s, she did a series of studies where she gave people problems, and she would ask them, much like the hot-cold game, how close do you feel that you are to a solution, right? So doing the funeral problem, you know, after 30 seconds, on a scale of 1 to 10, how close do you think you are? After a minute, on a scale of 1 to 10, how close do you think you are? And what she found was that people who solved the problem had no idea that they were close to solving the problem. So 10 seconds before they solved a problem like this, and she asked them on a scale of 1 to 10, how close do you think you are to solving that problem? They would tell her 1. I still have no idea whatsoever. Until they're like, oh my gosh, wait a second. She wanted him to come to another family reunion, and you snap all the way from 1 to 10, just like that. That's the insight problem. So we truly have no idea that we're close. Why is it? Well, let's consider the problem space. This is the problem space for a non-insight problem. This is the Tower of Hanoi. And again, in the Tower of Hanoi, as you are navigating through this problem space, you can tell, you can see, yeah, I'm getting closer to the solution. I used to have all 3 disks stacked on here. Now I got 2 disks stacked somewhere else. I'm getting closer to that solution. I used to have all 3 disks stacked over here. Now I got 2 disks. I'm getting close to the solution until you get to the goal state. So in a problem space like this, as you're navigating through the problem space, we are well aware that we're getting closer to our solution. We're well aware that we're making progress. So why is it that in an insight problem where you have your start state and you have one operator that you can apply, the cloth was a parachute, or one operator that you can apply, the sister was hoping that another family funeral would bring the individual. Why is it that that one step is so difficult? Well, the reason is because this is not the entire problem space in an insight problem. This is the problem space in an insight problem. So we have massive amounts of operators that we can apply. And we saw this with the haystack problem. So why did the cloth ripping make the haystack important? There were a number of operators that people tried to apply that made sense. They were legal operators. So they would say things like, maybe there was a needle in the haystack and they needed to sew up the cloth. Maybe they were going to sell the cloth and sell the haystack for money. But now that the cloth is ripped, the haystack is super important. Maybe they were carrying hay to the market in their cloth, and the cloth ripped, and now the hay is everywhere, so the haystack became important. So there are a number of different moves, all of which are legal, all of which could be done, none of which take you to the goal state. So the difficulty in these problems is the fact that when you apply your operators, and when you apply backup avoidance, when you apply hill climbing, you basically end up in dead end after dead end. And you have no idea if the next move is going to be the one that takes you to the goal state, or if you're going to have to go back and back again. So anytime that you're going to any of these, you don't feel any progress because you got to go back to the beginning after every single one. Eventually, you'll stumble upon that, at which point you're like, oh my gosh, made it to the goal state, one move, problem solved. So that's what makes a problem like this an insight problem, because there's no steps through the goal space. There's no intermediate solutions, right? There's nothing except that one step. That's what makes this so incredibly difficult, because there's no steps, between your initial state and your goal state. There's just that one operator, that one idea that is a correct idea that takes you straight to the goal state. So understanding insight problems is helped massively by understanding that this is the problem space that we're faced with insight problems. So no wonder, number one, they're difficult to solve. And no wonder, number two, you have no idea that you're getting close. Because we don't know if there's 100 of these, if there's 1,000 of these, there's 1,000,000 of these, and you don't know how many you've gone through until you finally hit that one that takes you to the goal state. All right, any questions about anything we've covered today? All right, so that's about it that I wanted to cover for today. So next time, we're going to start up on decision making. Make sure that you do your reflecting on part one, the gender gap. Make sure that you enter in your name when you click that link so that I can assign you grade for that. And then I will be posting part two on Monday so you can get started on that once you've completed your first part one. Other than that, we are done for today.